welcome to another module in this massive open online course. In this module, we are going to start looking at the Fourier analysis for discrete time signals and systems. So far we have looked at the Fourier analysis for continuous time, periodic as well as aperiodic signals. Starting with this module, we are going to start looking at discrete time periodic as well as aperiodic signals, alright. So, we are going to start looking at the Fourier analysis for discrete time, correct, for discrete time signals and discrete time signals and systems for that matter. Okay. So, the discrete Fourier series, now we are going to start with what is known as the discrete Fourier series. Now, the discrete Fourier series, this is defined for a discrete time periodic signal. This is designed for discrete time periodic signals similar to the complex exponential Fourier series and the trigonometric Fourier series that are defined for continuous time periodic signals. The discrete Fourier series is defined for a discrete time periodic signal. Okay. And so, we consider a discrete time periodic signal with period n naught such that x of n plus n naught equals x of n for all n. Then we say the discrete time periodic sequence, discrete time periodic signal is periodic with period equals n naught, alright. So, when there exists an n naught for a discrete time signal n such that x of n plus n naught equals x of n for all n, alright, we say alright the discrete time signal is periodic and its period is n naught, okay, alright. And for example, we have seen that the exponential signal, we have x of n equals e raised to the complex exponential signal e raised to j omega naught n, where omega naught equals is of the form 2 pi over n naught. This is a periodic signal with period n naught, that is you have x of x n equals e raised to j 2 pi by n naught of n, and if you looked at x of n plus n naught, and for that matter x of n plus k n naught, where k is any integer, this is e raised to j 2 pi over n naught n plus k n naught, which is equal to e raised to j 2 pi over n naught n into e raised to j 2 pi n naught. So, 2 pi k and e raised to j 2 pi k, this is equal to 1 for all k. So, this is simply e raised to j 2 pi over n naught times n, which is nothing but e raised to j omega naught n this is e raised to j omega naught n, which is basically x of n. So, we have x of n, in fact, we have x of n plus k n naught. Equals x of n. Okay. So, we have x of k n plus k n naught equals x of n for all n. So, which means this is a periodic signal, periodic discrete time signal, and the period equals n naught. Okay. So, e raised to j omega naught n, where omega naught is 2 pi n naught being an integer, is a periodic signal, is a discrete time periodic signal, and the period is n naught. Okay. Now, the discrete Fourier series representation is given as follows. We can, the discrete Fourier series representation is given as follows. So, consider a signal x n and the fundamental period, that is the smallest period, fundamental period equals n naught, then this can be expressed as x of n can be expressed as the sum of the complex exponential signals k equal to 0 to n naught minus 1 c k e raised to j k omega naught n, and these c k's are basically the coefficients of the discrete Fourier series. These are the coefficients of the discrete Fourier series or DFS. So, you can see that this can be expressed as a sum of a finite number of complex, unlike the complex Fourier series, which is the sum of an infinite number of complex exponentials corresponding to the fundamental frequency and its harmonics. This can be, that is a periodic discrete time signal, can be expressed as the sum of a finite number of complex exponential with frequencies 0, 2 pi over n naught, 2 pi over n naught times 2, so on and so forth, up to 2 pi over n naught times n naught minus 1. So, the frequencies of the complex exponentials are k times omega naught, k equals 0, 1 up to n naught minus 1. So, the frequencies are basically 0, 2 pi over n naught, 4 pi over n naught, so on, 2 pi over n naught into n naught minus 1. So, these are the discrete set of frequencies, all right, the set of frequencies. Okay. So, 4 pi over n naught, 2 pi over n naught minus 1, these are the finite set of frequencies. So, the complex, so basically, so the periodic sequence, the periodic discrete time signal with fundamental period n naught can be expressed as the sum of a finite set of complex exponential signals, all right, corresponding to the frequencies that are given as multiples of 2 pi over n naught, all right, integers ranging from 0 to n naught minus 1 of the fundamental frequency 2 pi over n naught. Okay. And now how to find this coefficients of the DFS, the discrete Fourier series, that is CL, what is the coefficient, the Lth coefficient of the DFS, and you can see that is given as follows. Now consider summation n equals 0 to n naught minus 1 x n e raised to j minus L omega naught n. This is equal to, substituting now the expression for the DFS, k equal to 0 to n naught minus 1 C k e raised to j k omega naught n into e raised to minus j L omega naught e raised to minus j L omega naught n, and now interchanging the summation. So, I have summation k equal to 0 to n naught minus 1, can take C k out since that depends only on k, summation n equal to 0 e raised to j k e raised to j omega naught k minus L into n. Okay. Now, you can see for k not equal to L, in fact this sum is equal to 0 for k not equal to, in fact for k not equal to L this is 1 minus e raised to minus j omega naught k minus L times n naught by 1 minus e raised to minus j omega naught e raised to minus j omega naught k minus L. Okay. And e raised to minus j omega naught n naught, that is 2 pi. So, this quantity here is 1 minus e raised to minus j k minus L in k minus L, and this quantity is 0, the numerator is 0 because e raised to minus j k minus L 2 pi is 1. So, this is basically when k is not equal to L, this is 0. So, the only case that is remaining is when k equal to L, when k equal to L, k equals L, this is e raised to j omega naught 0, which is 1. So, summation of 1 n equal to 0 to n naught minus 1, that is n naught. Okay. So, what we are left with is basically n naught if k is equal to L and 0 if k is not equal to L, and therefore, only the C k, the coefficient C k corresponding to k equal to L survives. So, that will be C L times n naught, which means we have summation n equal to 0 which means we have n naught into C L equals summation n equal to 0 to n naught minus 1 x n e raised to minus j omega naught e raised to minus j L omega naught n, which basically implies that your C L, the Lth coefficient of the discrete Fourier series, is 1 over n naught n equal to 0 to n naught minus 1 x n e raised to minus j L omega naught n. Okay. So, that is basically your discrete Fourier series coefficient. So, this is and you can also verify that this summation need not be over n naught equals 0 to n minus 1. In fact, this can be over any n naught contiguous sample. So, you can have this from n equals n naught, correct. So, this can be from 0 to n minus 1, or this can be from n equals 1 to n naught, or this can be from 2 to n naught plus 1. So, it can be, the summation can be taken over any contiguous n naught samples, okay, alright, and that I am representing it using this notation. So, summation can be over any contiguous n naught samples. The DC coefficient, and finally, you can see the DC coefficient. If you set L equal to 0, C naught equals 1 over n naught summation n equal to 0 to n naught minus 1 x n. So, this is the DC coefficient, simply the mean of the samples over a period. Over the single period n naught, all right. So, this is the mean of the samples, sample mean of the samples over a single period n naught, okay. So, this is basically the expression of, so this is basically the expression for the inverse discrete Fourier series, that is to extract the coefficients Ck's or the coefficient Cl from the periodic discrete time signal xn, okay, all right. And now coming to convergence, the discussion on convergence is going to be very brief. Now, the convergence, there are typically no issues, the convergence is guaranteed because it is a finite sum. Now, you can see basically both the discrete Fourier series, correct. If you can look at this expression for the discrete Fourier series. So, this is a finite sum. By finite sum we mean the summation over a finite number of elements, and as well as the inverse discrete Fourier series to evaluate the coefficient Cl, this is also a finite sum, correct. So, this is also a finite sum. So, because both the sums are finite, the convergence is guaranteed, all right. The convergence is guaranteed under certain very mild conditions, okay. So, the convergence is there are typically, because unlike both the continuous time periodic signal and as well as the continuous time aperiodic signals, because in the case of the continuous time periodic signal, it is a summation over an infinite series, there is a complex exponential Fourier series, and in the case of the continuous time aperiodic signals, it is integral over an infinite duration. Hence, in both those scenarios, it is important to ensure that the relevant summations or the integrals converge. However, since in this case both the summations are finite summations, that is a summation over a finite number of terms, the convergence is guaranteed, okay, all right. So, periodicity of the Fourier series coefficients, and you will also note that these Fourier series coefficients, the discrete Fourier series coefficients are periodic, that is very easy to see. you can see that Ck is 1 over n naught summation n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n. Now, if you consider C of k plus n naught, that is equal to 1 over n naught summation n equal to 0 to n minus 1 x n e raised to minus j k plus n naught omega naught n, which is summa 1 over n naught summation n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n times e raised to minus j n naught omega naught is 2 pi. So, this is 2 pi n and e raised to minus j 2 pi n is 1, and therefore, this again reduces to C k plus n naught reduces to 1 over n naught n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n, which is nothing but C k. So, we have C k plus n naught equals C k, sorry, this is capital N naught. This is for any general k implies the discrete Fourier series is periodic, implies the DFS coefficients are periodic. So, we have a discrete time periodic signal in time, and the corresponding discrete time Fourier series corresponding the discrete Fourier series coefficients in the frequency domain are also periodic, and the period incidentally is the same, that is the period is n naught for both the time as well as the spectral domain. And in fact, these quantities, these are known as the spectral coefficients, these quantities, the Ck's Ck plus n naught, these are known as the spectral coefficients of x n. These are known as the spectral coefficients of x n. All right. So, in this module we have started looking at the discrete Fourier series or the Fourier analysis for discrete time signals, and we have started with the discrete Fourier series for periodic discrete time signals. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.